Hello, Algebros. Today we're going to be talking about long division of polynomials. But to get us started, let's remind ourselves what long division looks like when we are dealing with just regular, plain old numbers. So I have a problem here. 21,540 divided by 10. Now, because it's divided by 10, we can find the answer really easily, but I wanted to use nice numbers to show you. So when we're dividing 10 into this number, we always want to look at the very first number. So can 10 go into 2? The answer is no. So because it can't go into 2, we now have to look at it here. So 10 can go into 21. 10 goes into 21 2 times. And so you take 2 times 10, and we get 20. And from here, we're subtracting that 20, and we get 1. 10 can't go into 1, so we bring this 5 down. 10 can go into 15 one time. 1 times 10 is 10. Then we subtract. 5 minus 0 is 5. 1 minus 1 is 0. 10 cannot go into 5, so we need to bring this number down. 4. 10 goes into 54. 5 times 10 is 50. We subtract 5 minus 5 is 0. 4 minus 0 is 4. 10 cannot go into 4, so we bring down the 0. 10 goes into 40 4 times. 4 times 10 is 40, and 40 minus 40 is 0. I'm sure you don't miss those days at all. But it's a good thing to remind ourselves what it looks like. Why don't we put this 2 over the 2? Well, it's because 10 cannot go into 2 by itself. It goes into this number. So we put those numbers over the value that we are dividing into, or the value that can be divided into. So we need to keep that in mind as we go through polynomial division. So we are taking 10r squared plus 65r plus 30 divided by 6r plus 6. So r plus 6 goes into 10r squared plus 65r plus 30. So now we're not just looking at a single value, we're looking at the value of the whole binomial. So r plus 6 cannot go into 10r squared by itself, because this is 2 terms and 10r squared is 1 term. So we have to look at the second term, and we're seeing how many times r plus 6 can go into 10r squared plus 65r, just like we did with that last problem with numbers. So because we're looking to see where r plus 6 can go into 10r squared, r can go into 10r squared 10r times. So we're going to put it over the 65r, just like we put the 2 over the 1 on 21 in our last problem. Okay. And just like we did the last problem, 10r times r would be 10r squared. 10r times 6 would be a positive 60r. So instead of multiplying this by one value, we have to multiply it by both values. And now we are still subtracting it. We are subtracting the whole line, not just 10r squared. So if this helps you out, you can put parentheses on it to help you remember. 10r squared minus 10r squared would be 0, which is what we wanted. If we didn't get 0 there, then we'd have to go back to the drawing board and find a different value. 65r minus 60r would be positive 5r. R plus 6 cannot go into 5r because 5r is a monomial and r plus 6 is a binomial. So we have to bring this value down, positive 30. And so we need to see how many times r goes into 5r. So r goes into 5r 5 times. Now we take 5 times r, which is 5r, 5 times 6, which is positive 30. And again, we are subtracting the whole line, so we are subtracting both terms. 5r minus 5r is 0. 30 minus 30 is 0. And we have nothing left to pull down. Nothing can go into 0. So we are finished. And what we just did was we just factored that polynomial. We know what 2 of the roots are now. We know 2 of the solutions. So I'm going to rewrite my answer down here. I'm not too concerned with fully factoring at this point. I want us to practice the division because you can factor this a little bit further, but that's not what the focus is today. The focus is practicing the long division and practice getting those factors by themselves. Okay. Number 2, we're going to take negative 4k squared plus 46k minus 90 and divide it by k minus 9. Again, k minus 9 as a binomial cannot go into a monomial, so we have to expand our vision and look at the binomial. So our value is going to go up here above. K goes into negative 4k squared, negative 4k times. So we're going to take negative 4k times k, which would be negative 4k squared. Negative 4k times negative 9 would be a positive 36k. So now we're subtracting that whole line, remember. Negative 4k squared minus a negative 4k squared would be 0. 46k minus 36k would be a positive 10k. And k minus 9 cannot go into 10k because k minus 9 is a binomial and 10k is a monomial. So we have to bring down the negative 90. And you have to ask yourself, what can I multiply k by to equal 10k? Well, the answer is 10. Positive 10. 10 times k would be 10k, and 10 times negative 9 would be negative 90. We're subtracting the whole line. Don't forget about that. The biggest mistake that students make is not subtracting every term and only subtracting the first term. 10k minus 10k would be 0. Negative 90 minus a negative 90 would also be 0. We're down to 0. That means we're finished. This is a factor. That is a factor. So I'm going to just rewrite it down here. Again, you can factor further, but that's not the focus of today. I just want you to practice the division. I don't want to overload you with too much. You're like, okay, well, that's cool, Ms. Bauer, but what does that even mean? Well, you can quickly check yourself if you really want to make sure that you have the right answer. We can check ourselves because if we multiply these two binomials together, we should get the original polynomial, in this case a trinomial that we started with. So let's just do that for kicks and grins. You don't have to do this, just showing you that everything that we are creating today is still equivalent. So k times negative 4k would be negative 4k squared. K times 10 would be positive 10k. Negative 9 times negative 4k would be positive 36k. And negative 9 times positive 10 would be negative 90. Combine your like terms here in the middle, which would be positive 46k minus 90. And this hopefully looks familiar because it is exactly what we started with. So again, we're factoring, we're pulling apart that multiplication, we're showing them for what they really are, if you want. We're revealing their true identities. We're taking off the facade of being a completed polynomial and pulling apart all of the pieces of their character, if you will. Right. So this is the answer that we're looking for. This was just to show you that this answer equals that. All right, I'm going to do a few more problems in the next video. Stay tuned. I know it's kind of a lot to absorb and a lot to take in at one time. So if you need to get up, walk around before you watch this next video, cool beans. Happy mathing.